So in the previous videos, we were talking about how we can have beams that are horizontal and that can have forces acting in multiple directions. But this is the first problem that we have where we're going to have a beam, or in this case a ladder, that is going to be at some angle. And what we're going to find is actually the process to solve this is exactly the same as it was for the previous problem. So this problem says that a ladder of mass capital M and length L is placed against a frictionless wall making an angle of theta relative to the horizontal. A person of mass M stands at a height of h above the ground of the ladder. Determine the normal force that the wall acts on the ladder, N sub W, the force the floor acts on the ladder, N sub F, and the force of friction that the floor acts on the ladder. Okay, so let's start here by drawing our free body diagram. So when we draw our free body diagram, it's going to look kind of like this. Okay, so here's our ladder. We know that there's going to be some force of friction. So this is going to be, or sorry, some force of gravity acting at the center of mass here. So this is going to be some capital mg acting straight down. There's going to be some force that the person is acting on the ladder. This is lowercase mg. We have some normal force that the wall acts here. So this is going to be, sorry, there you go. This is going to be some n sub wall. And then we have some normal force from the floor. So this is going to be our n sub f. The last force that we have is going to be the force of friction. So force of friction is going to keep this from sliding out. And so this is going to point in this direction. So now that we have our free body diagram here, what we can do is we can write our equations. So we can say then that the sum of the forces is going to be equal to 0, and the sum of the torques is also equal to 0. Okay, so now that we have this, we can expand it into our components in x and y. We can say that here's our x direction, here's our y direction. So sum of forces in the x direction is equal to, this is going to be n sub w minus f, which is equal to 0. And then we can sum our forces in y. Sum of forces in y is going to be equal to, this one is going to be equal to n sub floor minus lowercase mg minus capital mg. And then this is going to be equal to 0. Okay, sorry, I went off the screen a little bit here. So let's write this a little bit more compactly. So this is going to be minus lowercase mg minus capital mg is equal to 0. Okay, and we got it on there. So now that we have these two, we can sum our torques. So sum of torques. Now this is where things get a little bit tricky here. And always when we're summing our torques, we want to pick a point of rotation. I'm going to pick the point of rotation to be the bottom of the ladder because that's where we have two forces acting. So then, if this is going to be the angle of theta, then this right here is also the angle of theta. Because this is going to be 90 degrees and this is 90 minus theta. So this angle right here is theta. Likewise, this angle is theta. And then this angle is theta. So I'm labeling this because we're going to need this momentarily. So when we sum our torques, actually I'm going to write this a little bit lower here because I'm going to need a little bit more space. So when we sum our torques, we're going to have the sum of the torques is going to be equal to, remembering our convention for clockwise and counterclockwise. So counterclockwise is positive, clockwise is negative. So this mg right here is going to cause a counterclockwise rotation. So this is going to be plus mg times the distance that it acts. So this is going to be times L divided by 2. And then we need the component that's perpendicular to this R right here. So R by definition points from the point of rotation to where the force acts. The force that's perpendicular is actually the cosine of theta. Okay. Likewise, when we're doing this for our lowercase mg, we're going to see that this is going to be plus lowercase mg times some distance that we don't know yet. So let's just call that some distance, capital D, times cosine of theta. And then the last term, I'm in the way now, so this was actually probably not the best way to do this. So the last term that we're going to have here, so let's slide this over. I don't need alerts right now. So the last term is going to be from the normal force, okay? And in this case, this is going to be a sine component acting at the total distance. So this is going to be mg. Mg was this one. This one is going to be minus an L times n sub w times a sine of theta. And this whole thing is equal to 0. So let's figure out what this distance d is, okay? So here, I'm defining this distance of d to be like this, okay? So then we can say that sine of theta is really going to be equal to h divided by d. And so d is going to be equal to h divided by sine of theta, okay? So now let's set ourselves up so that we can solve this system. So the first thing that we can do is we can find what the normal force is, the floor is acting on the ladder. That's actually just from this equation, and this is completely separated. So we say then that n sub f is going to be equal to m plus m times g, okay? Then we have this. The next portion that we can do, and or at least think about at this point, is we can find the normal force from the wall, or set up a condition for it. The normal force from the wall is the same as the force of friction because of the sum of forces in x, right? The last thing that we can do here is we can solve for what the normal force from the wall is from this equation. So let's rearrange some things. So when we're looking at this, we have n sub w is going to be equal to, or let's not skip too many steps here. So n sub w times L times sine of theta is going to be equal to lowercase m g times d, which is going to be h divided by sine of theta. Cosine of theta divided by sine of theta is going to be a cotangent of theta. So cotangent of theta plus capital M g times cosine of theta. So this is going to be capital Mg times L divided by 2 times cosine of theta, okay? So then what we can do is we can divide both sides by L times sine of theta to find n sub w. So n sub w is going to be equal to, and I'm going to do a little bit of rearranging here. So I'm going to have a g times cotangent of theta common to both of these. This is g times cotangent of theta. And then I'm going to, this is not going to work out very cleanly. So this is going to be an mg divided by L. I already have my g on the outside. So this is going to be, oops, my undo is not cooperating with me right now. So this is going to be an m times h divided by L sine of theta plus capital M times just capital M divided by 2. Just capital M divided by 2. Okay. If you guys don't see how I did that, or if I made a mistake, check me. But this is what you should have for the normal force from the wall. All right. And then we know that the normal force from the wall is just going to be the same as the force of friction. So we have everything solved for now. Okay. So this is actually a pretty quick one here. But that's going to be it. All these problems are really the same. It's just a matter of practicing them. Okay. So that's going to be it for this video. Take it easy, guys.